In discontinuous conduction mode, the inductor current returns to zero and stays zero towards the end of the period. That means in all of the converters we have looked at so far, the inductor current is no longer forcing the diode to conduct. Therefore, we can no longer use the averaging method that we have looked so far to analytically derive the DC voltage transfer function, so V out divided by V in. However, the DC voltage across the inductor and the DC current through the capacitor still needs to be zero. But those equations don't help us here anymore to derive the transfer functions. From the previous assumptions that we have made, the two on this slide here are still valid. The first assumption puts the input power equal to the output power. That means we are assuming that the converters are 100% efficient, which is a fair assumption in power electronics. If we rewrite the input power as the input voltage times the input current, and the output power as the output voltage times the output current, we can rewrite the equation and solve for the output voltage. This is already a good start to derive the output voltage divided by the input voltage. So that's the transfer function that we actually want to know. So the two unknowns in this equation are the input current and the output current. The average output current is derived by Ohm's law across the resistor. So from the DC output voltage and the resistor, we already have the DC output current. So the more interesting one is the average input current. While these equations 1 and 2 here are generically valid for both the buck, the boost, and the buck boost converter and many other converters, we need to specifically look into the converter type to derive the average input current. For the buck converter, the inductor is connected between the DC input voltage source and the output capacitor during the on time of the switch. That means the inductor voltage is V in minus V out at that time. Taking Ohm's law across that inductor into account, we have the inductor voltage divided by the inductance, and using the derivative of the current waveform, so multiplying by the time duty cycle times the period time, which is down here, we can fully calculate this triangle and reach the peak current of the inductor. Now, in terms of a buck converter, this triangle also represents the input current, as the switch is not conducting later on anymore and the input current is going back to zero. So the average of the input current is actually the area under this triangle averaged over the time period t. The area of a triangle is the height of the triangle, I peak, times the base of the triangle, which is dt, and then halving the result. We just derive the peak current up here and putting it down here, multiplying it by the time base, d times t, and at the end averaging across the period time t and dividing by the factor of 2 because we have a triangular waveform gives us the average input current in a buck converter, which still is valid also in discontinuous conduction mode. Now we had the average output current from Ohm's law across the load. We have the average input current derived from the inductor current. And in equation 1, we have assumed that the converter is 100% efficient, which gives us V out, where the output voltage ended up being the input voltage times the input current divided by the output current. And that's exactly what we have derived in equations 4 and 2 here. Putting all these things together, we end up with this equation. To rewrite it a little shorter, I'm defining the factor alpha here. Alpha is dependent on the load resistance, on the inductance, on the duty cycle, and on the switching frequency or the period time t. That means we can rewrite the whole equation above into the quadratic equation down here, where V out is the dependent parameter that we want to solve for, and alpha and V in are just constants and are treated as such to solve the equation for V out. Now, solving the quadratic equation gives us the relation for the output voltage independency of the input voltage. And we can rewrite this equation in a simpler way as is shown down here in equation 59. Note that where we had in continuous conduction mode and in boundary conduction mode, the dependency of the output voltage as a function of the input voltage only on the duty cycle, we are now also dependent on the load or how much current the load is actually drawing, how we have designed the converter, so which inductance we have used, and at which switching frequency or period time t we are operating the converter. For the boost converter, we can use the same generic assumptions that the converter is, as in equation 1, 100% efficient, and we can always use Ohm's law across the resistor, across the load. But the voltages in a boost converter across the inductor are different. During the on time of the switch, we have the switch connected in parallel with the input voltage, the DC voltage source at the input, and we have Ohm's law across the inductor being rewritten over here, and again representing the derivative of the triangular inductor current. That gives us the peak of the inductor current, which is also the peak of the input current. But whereas the input current of a buck converter stopped at the duty cycle because the switch was interrupting it, the input current of the boost converter continues all the way until what I call here the magnetization period. So we have the duty cycle here, we have the magnetization times the period time t of the signal. So the input current in this case for the boost converter is the whole triangular waveform, and the average of that triangular waveform is the base, which is d plus m times the period time t multiplied by the peak of the triangle. And because the area is triangular, we divide by a factor of 2. And to take the average at the end, we divide by the period time t. That's why t is not showing up squared here, but only powered by 1. Now the factor m is still an unknown in this equation, and we need one more equation to derive an expression for m. And here we can use the fact that the DC current through the capacitor has to be 0. We know already the average output current, so the average current through the load. And that means that the average diode current in a boost converter needs to be equal the average output current that we already know from equation 2. But in this case, we're first going to derive an equation to express M as a factor of the output current. And for that, we can use the triangular part of the inductor waveform where the derivative is negative, because that's also the waveform that the diode is seeing as its current. The peak diode current is the same as the input current, and the base of that waveform is M times T, And if we average, we divide by the period time t. And because it's a triangular waveform again, we also divide by a factor of 2. Inserting the equation we derived for the peak inductor current from the last slide gives us an expression of the average output current as a function of only known variables, and M, which we together with Ohm's law across the load resistance finally can solve for M. We can put that equation for M into the equation number 4, which was the expression for the average input current of a boost converter. Furthermore, we divide it by the average output current, which is derived from Ohm's law across the load resistor. And the variables of the DC output voltage and the DC input voltage are the leftovers from equation number 1, where we assumed the converter to be 100% efficient. Once more, we can abbreviate all the dependencies into the parameter alpha, which is again the dependency on the load resistance or the current that the load is drawing from the converter, the way we designed the converter, so the inductance and the switching frequency, and the same as in the continuous conduction mode, also the duty cycle the converter is operating with. Finally, also for the boost converter, this leads to a quadratic equation which we can solve for V out in the next step and simplify it even more to express once again the DC output voltage as a function of the DC input voltage and the parameters summed up in the factor alpha. In a buck boost converter, the inductor is also shorted to the DC input voltage source during the conduction time of the switch. That means the input peak current is defined by the peak current of the inductor and Ohm's law applied to the inductor. Averaging that first triangle over time leads to the input current of a buck boost converter. This is once more the height of the triangle, so the inductor peak current times the base of that triangle, d times t, and at the end, averaged, that is divided, by the uppercase T, which is the period time. Therefore, D shows up from the upper equation here and squared as we also multiply it by the base, but T does not, as we actually average at the end over the period time T. As we did with the buck converter, we can also for the buck boost converter directly put the expression for the average input current, equation number 4, and the equation for the output current, the average output current, the load current, which was equation number 2, into our assumption that the converter is 100% efficient, which is equation number 1. And we once more end up with the dependency of the output voltage on the input voltage and the parameters of load resistance, inductance, period time t, and duty cycle. And we can rewrite the output voltage as an expression of the input voltage and what previously was defined in case of the buck and the boost converter as the square root of alpha.